In this lesson, we'll be exploring basic matrix operations. The learning objective is to execute commonly used built-in MATLAB functions that are designed for these basic matrix operations. And so the first thing that we need to reassess here is the matrix notation. And so this is a subscript notation that we use. And here we have in the matrix A, which we'll be dealing with quite a bit, we annotate this by hand by putting some brackets and then a big number often. And then the element-wise is a lowercase a with the subscripts I and j. And the subscript I is indicating which position that we're in on the rows. So I is equal to 1 would be the first row, I is equal to 2 would be the second row, and so forth, until we get to the last row, which would be I is equal to m. And then the subscript j are going to be the columns. So the first column would be j equals 1, the second column j equals 2, all the way to the last column, which would j equals n. And so that gives us that m rows and n columns, gives us the dimension of m by n. And so if given a matrix A, we'll type in the one from your sheet, in which we have the first row as 6, -2, 1, the second row as -2, 3, and 2, and the last row as 1, 2, and 8. Then we can obtain the dimensions of this matrix by typing in size A, and that'll give us two elements, the number 3 for the number of rows and the number of 3 for the number of columns. And using our index notation, if we want to get, let's say, this element here, this -2, that would be A, and then we would give it the row, which is the first row and the second column, and then our answer is -2. Similarly, if we had given it a row matrix of B, which is 1, 2, 7, and let's say a column matrix which is 9, 4, -1, and 3, then we can index these as, B, the third element here would be 7, and we could say B, the second element. We could also do B, the first row, and then the third element gives us 7 because the B matrix only has one row. And the C matrix, we could index it with a single number, so let's say C, the third element should be -1, and that's what we get. And we could also index this as saying C, third row, first column, gives us -1. And I've made mention of this before. When we're looking at these row matrices and column matrices, in mathematics and in MATLAB, these are often referred to as vectors, and I want to be deliberate about referring to these as matrices because in mechanics and in dynamics in particular, we discuss vectors as being something that has a direction and a magnitude. And in this case, B, we can call that a vector in math, but it's simply a set of 3 numbers. Or C, we can call that a column vector, but it's simply a set of 4 numbers. And it's only when you associate any of these numbers with what's called a basis or basis vectors that we can say that C would actually represent a vector or that B would represent a vector, according to mechanics. So we've already explored different sizes of matrices. And when we say that the size of A, for example, is a 3 by 3, then this would be a square matrix. And also notice that A has the same, so the diagonal terms 6, 3, and 8, and then the off diagonals, so in other words the 1, 2 position or 1, 2 element and the 2, 1 element are the same number. The 1, 3 and the 3, 1 element and the 2, 3 and the 3, 2 elements are all the same, so that indicates that A is actually a symmetric matrix. I mentioned a word just a moment ago about the diagonal of the matrix, and that's our 6, 3, 8. There's a command in MATLAB which comes in handy, we'll use it later, diag, and when we put in diag, the answer that it gives us are 6, 3, and 8, so it's pulling the diagonal out of a matrix. The term diag, or the command diag, can also be used the other way around, in which we can say diag, and let's do A11, A22, and A33. We can set this to a new matrix D. Whoops, I need to correct that. Inside the diag, I need to give it 3 numbers that are a matrix. And so by giving it this row matrix, you can see what it's done is it's taking the elements, any element that we want, which is 6, 3, and 8, and then it's created a matrix that is a diagonal matrix, meaning that it only has elements in the diagonal, and then the off-diagonal terms are equal to 0. And there is a special type of diagonal matrix in which with the diagonal matrix, the off-diagonal terms are always 0, and the special type of diagonal matrix in which all of the diagonals elements are equal to 1 is called the identity matrix. And so we can come up with an identity matrix by typing in EYE, in this case 3, we can do EYE 6, which would give us a 6 by 6 identity matrix. And the identity matrix is one which satisfies, and this is a defining property of the identity matrix, which satisfies that you have a matrix times the identity matrix is equal to the identity matrix times itself, and the matrix itself multiplied times the identity matrix is equal to itself. So this is the defining property, and in matrix mathematics, it's a diagonal matrix of 1s with 0 in the off diagonals. So cruising right along in our tutorial, let's talk about some matrix operations. And so for this, we're going to talk about the addition operation, where we have an A plus B is going to be equal to the matrix C. So let's go to our MATLAB window and let's create a B matrix. And in the B matrix, on our first row, we have 4, 7, -1. The second row as 2, -3, and 5. And the third row as -3, -2, and 9. So let's take a look at the addition property. So let's create a matrix C, which is A plus B. So we'll just say C is equal to A plus B. We get a new matrix of integers. And so we see that when we add matrices, the matrices must have the same dimensions. A and B are each a 3 by 3, so we satisfy that. And we also see that matrix addition is associative. So if we take A plus B and then add C to this, then the grouping itself isn't going to matter whether we have A plus B grouped together plus C, or if we have A plus B plus C grouped together. And so we'll get the same answer in both. In addition, addition has the commutative property, which is that if we have A plus B, then this is equivalent to B plus A. And a slightly more sophisticated way to do this is using a MATLAB built-in function called isEqual, where we're going to test two expressions placed on the left-hand side and right-hand side of the comma. And so we can go back up to what we did with our associative property. We can say is A plus B grouped together plus C equal to A plus open paren B plus C close paren. And so if this is true, our logic should be 1. And we can do the same thing by looking at the commutative property, where we're testing whether A plus B is equal to B plus C. Pardon me, that's wrong. A plus B is equal to B plus A, and then this should be correct. So now if we flip over and we're looking at matrix subtraction, where we'll be subtracting each element of the matrices, and we get the matrix C is equal to A minus B. We have the same requirement, which is that A and B must have the same dimensions. And then let's take a look at the associative and commutative properties here, in which if it's associative, then that means that A minus B plus C is going to be equal to A minus B plus C. And because subtraction is not associative, whether we're talking about matrix subtraction or just a real number subtraction, it isn't associative. And we also see that, let's check out the commutative property, is A minus B equal to B minus A. And we'll see here that the commutative property is also not satisfied with subtraction. Next is multiplying a matrix by a scalar. And all that's going to do is, if we've got a scalar G multiplied times the matrix A, it's going to scale every single element by that value G. So if G is equal to 0.5 and we have G times A, this is acting as a scalar multiplier, and we've simply just halved each of the elements within the matrix. This operation, where we're multiplying by a scalar, is commutative. So G times A, that we did just a moment ago, is equivalent to A times G. And so our next step in this series is looking at matrix multiplication. In a matrix multiplication, where we have the matrix C is equal to A times B, then this is given by this expression where we're summing from k is equal to 1 to n. And remember that n is the dimension of the number of rows, and each element, the row element and then column element, Cij, is going to be equal to the summation from k is equal to 1 to n of A sub I k and B sub k j in index notation. And so this is where, well, I said just a moment ago, sorry, n is the column dimension, so it's the number of columns in A, and it's also the row dimension of B. So let me make that clear. N is equal to the column dimension of A and the row dimension of B, because we need to have an m by n and then an n by some other number to be able to make this work. So let's do that. Let's do C is equal to A times B. And because both of these are symmetric matrices, and it's an m by m, or a 3 by 3 multiplied times a 3 by 3, the dimension of the product, matrix multiplication, was going to be a 3 by 3. And the summation that we saw just a moment ago, because we multiplied A times B, is taking each column in B, multiplying it by each row, just like a dot product, where the first element in the first column will be multiplied times 6, so 4 times 6, and then 2 times negative 2, and then negative 3 times 1, and we add them all up, and that looks just like a dot product. And that's also why another name for this matrix multiplication is called an inner product, and a dot product is an inner product. So this may ring some bells for those of you that have seen this in your mathematics classes. Now, we just did A times B, and MATLAB recognizes this multiplication operator as a matrix multiplication. Now, if we wanted to take A times B, but we wanted to simply multiply 6 times 4 and put it in the first element, negative 2 times 7 and put it into the first row second column, and then 1 times negative 1, put it into the first row third column, and so forth, all the way down to the third row third column, 9 times 8. Then instead of using A times B, we would use A dot times B. And so this is called an element-wise multiplication or scalar multiplication. And we've used this before when inserting long row vectors or row matrices, column matrices into other functions, where we need to take the square root, if we need to take a square, or we need to multiply two matrices together. All right, so a couple of other operations that we're going to work with are going to be the matrix inverse. And a matrix inverse is one that satisfies that A inverse multiplied times A is equal to the identity matrix. And so to be able to do this, the matrix A must be non-singular. the determinant, which means that the determinant can't be 0. We're going to be talking more about determinants, inverses. You'll be coding even just the matrix multiplication in an assignment for next time. And so let's talk about the non-singular element here. The determinant needs to be non-zero. And so if we have A, we can type in det of A, and that gives us the determinant, which gives us a single number. The determinant of this matrix is 77. It is non-zero, so therefore we can take the inverse of A. These are all things that we'll talk about later. The command for inverse in MATLAB is INV, and then with this we can show that this is correct, because if we type in INV, the inverse of A, multiplied by A, then we should get the identity matrix, which is a diagonal matrix, so zeros in the off-diagonal terms and 1 along the diagonal. Okay, the next operation is called transposition, or the transpose of a matrix, and this is transforming all the rows into columns and the columns into rows. So if we have the elements A11 and A12, our first two elements within the A matrix, that when we do the A transpose, which is a right superscript T, then we see that the A12 element that was in A becomes the 21 element, which is now in the A transpose. And the way that we do this is A transpose is A, and then we give it the single quote, or the A prime. So here's our matrix A, and if we do A transpose, our diagonal terms remain the same. And I guess that's actually not giving us much here, because A is a symmetric matrix. Let's look at B, and let's do the transpose of it. So we have allowed our diagonal to be the same. B, 4, -3, and 9, and 7 is now in the, which was in the 1, 2 position, is now in the 2, 1 position. -2, which was in the 3, 2 position, is now in the 2, 3 position, and -1, which was in the 1, 3 position, is now in the 3, 1 position. So we've essentially flipped this matrix across the axis, or across its diagonal. All right, so one last operation before we wrap up is called matrix augmentation. And matrix augmentation is where we're adding a column or a series of columns, a row or a series of rows to an existing matrix. And so here we're saying that our matrix C is equal to the augmentation of A and B. And so augmentation means that we're adding to something. And so you can see here that we have all the elements of A indexed, and then a line, and then the elements B, 1, 2, and 3. And so this augmentation takes a 3 by 3 and then takes a 3 by 1 column matrix and turns it into a 3 by 4. So let's take a look at what we have here. We have A and we have B. B we've already defined in our MATLAB script as a row matrix, so we're going to use this instead as a column matrix. And notice that we use the prime, the B prime, which is the transpose operator, to turn this into a column. And if we want to augment this, so C is equal to the augment of A and B together, then we need to put them together. It's going to be a new matrix, and a matrix is simply a suitcase that's storage for whatever we need. We need A on the left side and we need B on the right side, which means that we put a comma in between them. And our, I need to turn my B into a column matrix. And so now we see that we get a 3 by 4. Okay, there's my A matrix, there's my B matrix that was left. You can also augment above or below. So let's make a D in which we're augmenting A above B. And that means that A is going to be my 3 by 3. That's in the first 3 rows, and then B will be my 1 by 3 that's in the last row, and so the dimensions here are 4 by 3. Okay, now this wraps up the discussion on just the basic matrix operations and matrices. I encourage you to explore what this looks like in several different types of matrices. Make sure that you understand each of these commands. And what we'll be doing over the next couple lessons is we're actually going to be decomposing what's happening in these matrix operations. So what is a determinant? What is matrix multiplication? What is a matrix inverse? Because it's nice just to be able to say I in V and it just does my inverse, but what's actually going on in MATLAB itself to make those calculations?